Hi, today I am going to discuss about basic working of a transformer. Last class we have discussed that current relationship or the flux can be utilized to develop induced EMF across a coil. There are three ways to develop induced EMF. First one is vary the magnitude of the magnetic field, keeping coil as a stationary. Second one, moving the coil, keeping magnitude of the field strength constant. Third one, vary both the magnetic field as well as the coil. So basic three ways to obtain induced EMF, or you can say these are the ways by which electrical energy is converted to mechanical energy or mechanical energy is converted to electrical energy. Today we will discuss about transformer only based on whatever we have discussed in last class. So this is nothing but Faraday's laws of electromagnetic induction. It is derived from there that the E proportional to d psi dt. Psi is nothing but flux linked with the coil. So if flux linked with the coil changes, then only EMF will be induced. Now the flux linked with the coil can be expressed as N into phi. I is nothing but magnetic lines of force in Weber. N is the number of turns. So by increasing the number of turns, also we can increase the induced EMF, and this property is used in case of transformer. We know that across a transformer, single phase transformer, two windings are there, primary winding and secondary winding, and if we are increasing the number of turns of the secondary winding, then secondary winding voltage increases. Now little bit in detail we will discuss this one. In every case, direction of the induced EMF will be such that it will oppose the cause, and the cause is here change in flux linkage. Now the change in flux linkage can be obtained in following three ways. As already we have discussed, changing the magnitude of the flux linking a static coil, moving the turn outside the region of the static field, moving the turn and changing the flux simultaneously. Today we will consider this first case. Let's see. Here it is a representation by which we can explain all motor, generator, transformer, induction messages, everything. This dotted point indicates direction of the magnetic field coming out of the screen. This is direction of the current flowing through the conductor, or you can say coil. So this is, for simplicity, one turn coil. This is movement of the coil. All three are perpendicular to each other. You can apply Fleming left hand right hand rule to find the unknown parameters or the movement of the conductors. Here in case of transformer, we know that turns are stationary or the coil is stationary. Magnetic field we have to change. The magnetic field we can change by applying a sinusoidal voltage across the primary winding of the transformer. So the current will be sinusoidal, and the sinusoidal current magnitude is always changing from 0 to pi by 2. It is increasing, then pi by 2 to pi it is decreasing, then in the reverse direction pi to 2 pi it will be negative, then 0. So in case of sinusoidal signal, the current is varying, and because of that current the magnetic lines of force are generated, or the magnetic field is developed, that is also varying in nature. So let's explain these things mathematically. So B, uniform flux density in Tesla. So B is nothing but uniform flux density in Tesla. Later on we will consider this one sinusoidal. So flux density is nothing but flux per unit area. So here you can say this is the length of the conductor in the region of magnetic field. N is equal to one rectangular loop of one turn. So this is only one turn. X moment of the conductor, and the flux lines conductor and the motion are mutually perpendicular. So this flux lines coming out of the screen, it is going upward, and this one the right hand side. So these three are perpendicular to each other. Then the flux linkage of the loop is equal to B into L into N, Weber turns. So this is very important relationship. You have to recall this one many times. So keep in mind this one. So flux linkage is BLN Weber turns. Based on this one, as flux linkage is this one's because the EMF and is equal to d psi dt. So this you can say psi and d psi dt. Out of this, there may be B phi may change. Then the movement because of that, this movement of the conductor also we will explain in case of generator and motor, as well as in induction machines. So later we will consider. So right now we are discussing about this first case, changing the magnitude of the flux by applying a sinusoidal voltage across an electromagnet. Static coil. This is your stationary. X is equal to 0. See, B is equal to uniform flux density in Tesla, N is equal to one rectangular loop on one turn, L is equal to length of conductor. So this is your length of the conductor. This one. If the flux is unchanging and the conductor is stationary, no EMF will be developed at the terminal of the loop. So across this point, voltage will be 0. So let's consider this B is equal to Bm cos omega t. Just for simplicity, I have taken this is your sinusoidal or cosinusoidal magnetic field. So B is equal to Bm cos omega t. So to obtain this one, obviously we have to apply AC sinusoidal voltage across the electromagnet. So let's start from this point that B already we have got Bm cos omega t and conductor is stationary. Then the EMF induced E is equal to d psi dt. So d dt of psi is equal to how much? Psi is equal to Bm cos omega t into L into L. So this Bm is maximum or peak, as we know that in case of sinusoidal signal we are representing this Bm sin omega t or cos omega t. So that peak is Bm. Then L length of the conductor and N number of turns are constant. And the differentiation we will get minus Bm sin omega t. So this is what alternating voltage we will get across this terminal. So this is applicable to transformer. We can now correlate this one. That in case of transformer, primary winding is connected with a AC supply, developing this sinusoidal magnetic field Bm cos omega t. Now the secondary winding is stationary, having n number of turns. Then the EMF induced across the secondary winding terminal will be minus Bm sin omega t into L into N into omega. Similarly, in case of motor and generator, we will see, as well as in case of induction machine also we can explain based on this structure. Only thing is that we have to develop this induced EMF. Okay, so today we have discussed just basics of transformer. To develop varying magnetic field, or you can say electromagnet is to be created, and that is obtained by applying a sinusoidal voltage across a primary winding of the transformer. Then across the secondary winding, based on our calculations and derivations, EMF will be induced. From later classes we will discuss about basics of DC motor, generator and induction machines. Thank you.